Dear students, welcome to the EPG Pathshala. I am Dr. Rajkishore Sharma, an Associate Professor in Chemistry Department of University of Delhi. Today, we are going to discuss about the module Analysis of X-ray diffraction data under the paper of Surface Analytical Techniques 2. X-ray diffraction or XRD analysis is an analytical technique designed to provide more in-depth information about crystalline compounds, including identification and quantification of crystalline phases. This is a useful tool when we want to identify a contaminant or corrosion product, or for identification of foreign phases for purity analysis of crystalline powders. X-ray diffraction pattern is the fingerprint of the periodic atomic arrangements in a given material. The topics which we will discuss today: information in a diffraction pattern, data collection and the analysis, indexing a powder pattern, initial phasing, reciprocal lattice vector, structure factor, system abscences, intensity of diffracted beam and lattice strain. Type of information in XRD analysis. Some experimental results to analyze. We have used two experimental results here. For example, polyaniline in polyaniline nanosheets and despacing of the carbonized polyaniline nanosheet samples. The other experimental result we have included here is the X-ray diffraction pattern of alpha nickel cobalt hydroxide over nickel shells. So there is an experimental result in which we use nickel shell as a substrate and coated nickel cobalt hydroxide over it, and we will discuss the XRD analysis of this sample. In the third, we use vanadium oxide nanostrips coated over graphene materials. X-ray safety will also be discussed. XRD analysis is based on constructive interference of monochromatic X-rays and a crystalline sample. The X-rays are generated by a cathode ray tube filtered to produce monochromatic radiation, collimated to concentrate and directed towards the sample. The interaction of the incident rays with the sample produce constructive interference when conditions satisfy Bragg's law, that is n lambda is equal to 2d sin theta. This law relates the wavelength of electromagnetic radiation to the diffraction angle and the lattice spacing in a crystalline sample. The characteristic X-ray diffraction patterns generated in a typical XRD analysis provides a unique fingerprint of the crystals present in the sample. When properly interpreted by comparison with standard reference patterns and measurements, this fingerprint allows identification of the crystalline forms. Information which we get from a diffraction patterns are: number 1, the phase identification; number 2, the crystal size; number 3, crystal quality; number 4, texture to some extent; 5 is the crystal structure. First of all, we will discuss the sample preparation for X-ray diffraction analysis. All types of powder diffraction analyses are non-destructive. The XRD measurement requires about 1 gram of the powder sample. Intensity aberration minimization of samples with large unit cells may require about 5 gram of a material. Generally, 5 gram of sample material is preferred, although quantities as gram as 0.25 gram can be analyzed. For routine qualitative analysis, approximately 1 gram sample is sufficient for the diffraction analysis. In case of well crystalline single grain sample, about 1 milligram of the material is sufficient. For bulk sample analysis, where certain fraction is to be extracted, we require preferably more than 10 gram of the sample. Neutron diffraction requires normally larger amounts sample, that is 5 to 10 gram. The sample should be representative of bulk material and should be crushed to less than 50 micron powder. Now, we will discuss about the steps involved in interpretation of the diffraction data. First of all, 2 theta range is to be selected, in which we need to record the diffraction pattern. Then, step size and time per step is to be selected. Then hardware test is done, which involves slit size, filter and sample alignment. Once hardware test report is okay, then fast scan is followed with a slower scan. Then we look for fluorescence. After the data is collected, then the normalized data is used for comparison. Main application of X-ray diffraction analysis includes the nanomaterial. We look for phase composition, crystallite size and shape. We look for lattice distortions and faulting. We test compositional variations, orientation, in situ structure development, etc. This technique is also used in reservoir core analysis, fuel quality testing, new material research and development, polymers and composites, pharmaceuticals and organics, polymorphs, crystallinity and orientation. We will discuss one of the applications, that is nanotechnological research involving material structure analysis via X-ray diffraction. Nanotechnology research and X-ray analysis is applied to the understanding of characteristics of nanomaterials and nanostructures for their crystallinity, semicrystalline nature, amorphous character, etc. This is used in industries such as glass and polymer industry and requires specialist understanding for interpretation of results. Analysis of peak shape give information about crystallite size and other aspects of microstructure, particularly lattice distortions due to the composition or microstrain variation and faulting. XRD provides an adaptable method for measuring crystalline phase, degree of crystallinity and structure. Crystalline orientation is another important parameter that is provided by the X-ray diffraction technique. We will discuss how to analyze the data obtained from X-ray diffraction. Using mathematical technique of Fourier transforms, the recorded series of two-dimensional diffraction pattern is converted into three-dimensional model of electron density. The first step is data processing through indexing reflections. This means identifying the dimension of the unit cell and the peak corresponding to which position in the reciprocal space. Symmetry of crystal, that is space group, is determined by the byproduct of indexing. Indexing is generally accompanied using an auto-indexing routine. The data is then integrated over assigning the symmetry, which results in conversion of hundreds of images containing the thousands of reflections into a single file. A full set of data contains hundreds of separate images taken at different orientations of the crystal. Now, an important step in data analysis is the indexing. Indexing is the process of determining the unit cell dimensions from the peak positions. To index a powder diffraction pattern, it is necessary to assign the Miller indices, that is HKL, to each peak. A diffraction pattern cannot be analyzed until it has been indexed. It is always the first step in analysis. Unfortunately, it is not just the simple reverse of calculating peak positions from the unit cell of dimensions and wavelengths. For lower symmetry structures, that is orthorhombic, monoclinic or triclinic, it is usually necessary to use a computer algorithm. This is called auto-indexing. Manual indexing consists of the following steps, that is, to determine d-spacing of each peak from its 2 theta value using Bragg's law. To create a table of 1 upon d, create a table of 1 upon d2 values for each peak. Then look for a common factor, that is 1 upon a and 1 upon a2, that can be divided into each of the 1 upon d into each upon 1 upon d2 values. Now we will discuss the initial phasing. The data collected from a diffraction pattern is a reciprocal space representation of the crystal lattice. The position of each diffraction spot is governed by the inherent symmetry within the crystal and by the shape and size of the unit cell. The intensity of each spot is recorded and is proportional to the square of the structure factor amplitude. The structure factor is defined as the complex number which contains information relating to both the phase and the amplitude of the wave. The phase cannot be recorded directly during the experiment and This is known as the phase problem. The initial phasing can be divided into different ways. Number 1 is ab initio phasing or direct methods. Number 2 is the molecular replacement. Number 3, anomalous X-ray scattering, which is also known as MAD or SAD phasing. The fourth is heavy atom methods. These are multiple isomorphous replacements. Now we will discuss the reciprocal lattice vector. The reciprocal lattice represents the Fourier transform of another lattice, usually a Bravais lattice. In normal usage, the first lattice, whose transform is represented by the reciprocal lattice, is usually a periodic spatial function in real space and is also known as the direct lattice. While the direct lattice exists in real space and is what one would commonly understand as a physical lattice, the reciprocal lattice exists in reciprocal space and also known as momentum space or less commonly K space. The reciprocal lattice plays a fundamental role in most analytical studies of periodic structures, particularly in the theory of diffraction. In neutron and X-ray diffraction, due to the Laue conditions, the momentum difference between incoming and diffracted X-rays of a crystal is a reciprocal lattice vector. The diffraction pattern of a crystal can be used to determine the reciprocal vectors of the lattice. Using this process, one can infer the atomic arrangement of a crystal. The structure factor is a mathematical function describing the amplitude and the phase of the wave diffracted from crystal lattice planes characterized by Miller indices HKL. The structure factor is a critical tool interpretation of scattering patterns, that is, the interference patterns obtained in X-ray diffraction, electron and neutron diffraction experiments also. The intensity of a diffracted beam is directly related to the amplitude of the structure factor, but the phase must normally be deduced by indirect means. In structural determination, phases are estimated and an initial description of the position and anisotropic displacements of the scattering atoms is deduced. From this initial model, structure factors are calculated and compared with those experimentally observed. Iterative refinement procedures attempted to minimize the difference between calculation and experiments until a satisfactory fit has been obtained. As we can see from the image shown in this slide, some lines are absent from the intensity versus 2 theta graph. This is because every transition is not allowed. There are certain restrictions which are as follows. Number 1, for cubic lattice, all transitions are allowed. Number 2, for phase-centered cubic system, allowed transitions are where HKL are all odd or all are even. As we can from the graph, only 111, 200, 220 and 222 is allowed. Rest are restricted and we can say as these as system absences. For body-centered cubic system, that is H plus K plus L should be even. If H plus K plus L is odd, we do not get any transition. If the lattice is not primitive, certain classes of Miller indices, that is HKL peaks, will be missing. These are called systematic absences and we can use them to determine the space group. The permitted reflections are shown in image. For simple cubic 100, 110, 111, 200, etc. are the permitted reflections. For body-centered cubic 110, 200, 211, 220, etc. are the permitted reflections. For FCC, that is face-centered cubic 111, 200, 220, etc. are the permitted reflections. Discuss the diffraction pattern of a NaCl crystal. The diffraction pattern of NaCl crystal in a tube facing X-ray beam. Each peak in the pattern represents a particular plane. As we can see, various planes are shown in the pattern, that is 111, 200, 220, 311, etc. The d-spacing of each peak is then obtained by solution of Bragg's equation for the appropriate value of lambda. Once all d-spacings have been determined, automated search or match routines compare the d-spacing of the unknown to those of known materials. Because material has a unique set of d-spacing, matching these with d-spacing provides an identification of the unknown sample. A systematic procedure is used by ordering the d-spacings in terms of their intensities, beginning with the most intense peak. Files of d-spacings for hundreds of thousands of inorganic compounds are available from the International Center of Diffraction Data as the powder diffraction files. We call them PDF. Many other sites contain d-spacing of minerals, such as the American Mineralogist Crystal Structure Database. Commonly, this information is an integral portion of the software that comes with the instrumentation. In the absence of all other factors of the intensity of the diffracted X-ray is equal to the square of the structure factor. But there are a number of other factors that affect the intensity. The first is polarization factor. The second one is structure factor. We have already discussed about this. The third is multiplicity factor. The multiplicity factor refers to the relative proportion of the planes contributing to diffraction. More the number of planes, greater is the intensity. Compare diffraction from the 100 and 11 set of planes of a cubic crystal. The 100 family has 3 planes, that is 100, 010 and 001 with the d-spacing but with different orientations. The A11, the 111 family has 4 planes with the same d-spacing but different orientations. These are all 111, 111, 111 and the last one as 111. Thus, everything else begin the same. The ratio of intensities from 100 and 111 planes will be in the ratio of 3/4. The fourth is Lorentz factor. The Lorentz factor is a trigonometric factor that relates to the distribution of planes as function of 2 theta. For a powder sample with randomly oriented particles, the integrated intensity, that is area under the curve, of a reflection at a given Bragg angle depends on the number of particles with that orientation. Even though the particles are oriented at random, this number is not a constant but depends on the value of the Bragg angle. The fifth is absorption factor. The X-ray intensity also depends on the absorption of the specimen being investigated. This also depends on the geometry of the setup. In the case of diffractometer, the absorption factor is independent of the Bragg angle and does not affect the relative intensities of different lines. The sixth is temperature factor. Atoms in the lattice are constantly vibrating about their equilibrium position. As the temperature increases, this vibration amplitude increases. One effect of this vibration is that the lattice spacing constantly changes so that the overall intensity of a line decreases with increasing temperature. At the same time, background scattering increases. For a given temperature, this effect is pronounced at higher Bragg angle since the d-spacing is smaller. The temperature effect is usually determined experimentally and is written in the form of exponential minus 2m. When crystallites are less than approximately 1000 angstrom in size, appreciable broadening in the X-ray diffraction line occurs. These regions may in fact correspond to the actual size of the particles. At other times, however, these regions form domains in the larger particle and may be a distinguishes an important feature. In either case, the observed line broadening can be used to estimate the average size. In the simplest case, where the particles are stress-free, the size is estimated from a single diffraction peak. But in those cases where stress may be present, a more robust method involving several diffraction peaks is required. As it is seen from the image, as the strain increases, broadening of peak occurs. The formula of broadening is also given there. Now about d-spacing of lattice planes. It depends on the size of the elementary cell and determines the position of the peak. Each peak measures a D spacing that represents a family of lattice planes. Now about intensity of each peak. This is caused by the crystallographic structure, that is, position of the atoms within the elementary cell and their thermal vibrations. Line width and the shape of the peak derived from the particle size and particle size of the sample material under testing. Relative position of the diffraction peak. It depends on the size and shape of the unit cell and provides information about the location of the lattice planes in the crystal structure. Now the type of information by X-ray diffraction analysis. The kind of material that compose a solid. This information is called qualitative analysis. The second is the quality of material that compose the solid. It is called the quantitative analysis. The third is the quality of materials that are crystallized. So it is called the crystallinity. The amount of stress present in the solid, this is known as residual stress. The size of the crystallite that compose the solid, it's called the crystallite size. Average orientation of the crystallites that compose the solid are known as texture. Is a case study where we will discuss the X-ray diffraction patterns of polyaniline nanosheets, and that is abbreviated as PNS, and de-spacing of the carbonized PNS, that is polyaniline nanosheets. So in this research, researchers they took nanostructured polyaniline and they carbonized it at different temperatures. So we will see the corresponding effects on the X-ray diffraction. Here, as you see in the diffraction patterns, PANI or the polyaniline, the prominent peak at 2 theta of 14.5, 19.6 and 25.5 are associated with 001, 020 and 200 planes of emeraldine salt of polyaniline. After pyrolysis, the pyrolyzed samples show characteristic peaks of carbon corresponding to 002 plane at 21 degree, and the de-spacing calculated from this peak are shown in the figure. Intensity of de-spacing shows an increase from PNS to the carbonized PANI, that is NCNS, carbonized at 400 degrees centigrade. So the de-spacing in this case is 0.45 nanometer. However, on further increasing the temperature, a decrease in de-spacing to 0.4 nanometer, that is in case of carbonizing it at 500 degrees C. On further increasing the temperature to 600, the de-spacing is noticed at 0.37 nanometer. Pyrolyzed samples show characteristic peak of carbon corresponding to 002 plane at 21 degree, and the de-spacing calculated from this peak are shown in figure. Interestingly, the de-spacing shows an increase from PNS, that is 0.33 nanometer, to NCNS 400, that is 0.45 nanometer. So there is an increase in de-spacing. However, on further increasing the temperature, a decrease in the de-spacing to 0.45 nanometer, that is for the sample carbonized at 500 degrees C, and 0.37 for the sample which is carbonized at 600 degrees C is noticed. So the change in de-spacing is observed because of the structural changing at different temperature annealings. Depicts another case study of alpha nickel cobalt hydroxide on nickel shells. Here the 2 theta peaks at 11.1, 16.8, 19.2, 33.8, 38.4 and 59.5 well coincide to 003, 100, 006, 101, 015 and 110 reflections of alpha nickel cobalt hydroxide. The interlayer spacing calculated from 003 reflection is approximately 8 angstroms, that is the typical signature of the presence of intercalated ions in alpha phase. Further, 003 and 006 diffraction peaks are quite similar, whereas the diffraction peaks assigned to 101, that is de-spacing is 2.68 angstroms, has a sawtooth shape which is a characteristic feature. The above features are the typical characteristics of turbostatic phases.
The diffraction pattern of synthesized CA-PANI, that is carbon aerogel, and PANI, polyaniline nanocomposite. Two broad characteristic peaks centered at 2 theta, value of 24 and 43 are observed in X-ray diffraction patterns of carbon aerogel, which can be indexed to 002 and 100 graphitic planes.
The most intense peak observed at 2 theta value of 24.5 exhibit enhanced d-spacing, that is 3.63 angstrom, than that of typical graphitic geometry, that is 3.4 angstroms. The diffraction pattern of synthesized carbon aerogel polyaniline nanocomposite shows 5 typical peaks at 8.7, 14.9, 20.5, 25.3, 27.1, corresponding to 001, 010, 011, 020 to 00 planes of the polyaniline. Peaks at 20.5 and 25.3 are attributed to periodicity parallel and perpendicular to the polyaniline polymeric chains respectively.
The researchers have synthesized vanadium oxide nanostrips on graphene nanostructures. So LGONR refers to the Lattice graphene oxide nanoribbon. Lattice represents the whole structure of the graphene nanoribbon. So here for LGONR, diffraction pattern shows 2 peaks at 2 theta is equal to 9.8 and 43.5 corresponding to 002 and 100 lattice planes respectively. The diffraction patterns in figure reveals characteristic peaks of vanadium oxide at 2 theta is equal to 20.3, 27.3, 28.2, 28.8, 32.6, 38.6, 41.2, 47.7, 51.7, 59.8, 61.2 and 70.4. These are indexed to an orthorhombic lattice structure and matches well with the JCPDS card number 00009037. JCPDS refers to the Joint Committee Powder Diffraction Samples. The diffraction peaks of JNR at VOS, vanadium oxide on graphene nanoribbon composite, occurs at 11.2 and 17.4, 21.8, 23.7, 5.6, 27.2, 28.5, 48.4, 50.7, 59.5, 61.9, 66.8 and 69.5. The diffraction pattern of JNR at VOS highlights better resolved diffraction peaks with enhanced intensity compared to vanadium oxide nanostrips, suggesting improved crystalline nature when it is deposited on the graphene nanoribbons, shows the nanostructured morphology. Now there are some points to remember. X-rays are extremely dangerous and must be handled with caution. They are dangerous because they penetrate the human body and breaks up the molecules of DNAs. Also, the skin will be singed like a sunburn. However, after the breaking of DNA molecule, if they join in wrong way, it can lead to cancer.
Now, let's summarize all the content that we have learned today. X-ray diffraction or XRD analysis is an analytical technique designed to provide more in-depth information about crystalline compounds, including identification and quantification of crystalline phases. This is a useful tool when trying to identify a contaminant or corrosion product and for identification of a foreign phase for purity analysis of a crystalline powder. As said before, the X-ray diffraction pattern is a fingerprint of the periodic atomic arrangement in a given material. The interaction of incident rays with the sample produces constructive interference. When conditions satisfy Bragg's law, that is n lambda is equal to 2d sin theta. Using mathematical technique of Fourier transform, the recorded series of two-dimensional diffraction pattern is converted into a three-dimensional model of electron density. The first step in data processing is indexing the reflections. This means identifying the dimensions of the unit cell and which peak corresponds to what position in the reciprocal space. The structure factor is a mathematical function describing the amplitude and the phase of a wave diffracted from crystal lattice plane characterized by Miller indices. The structure factor is a critical tool in the interpretation of scattering patterns obtained in XRD. The reciprocal lattice represents the Fourier transform of another lattice, usually a Bravais lattice. Thank you.